Hey guys, welcome to the tutorial video on Gauss's law for concentric objects. I'm going to have this same intro part for both of the videos, so if you're going to watch them both back to back, then that means go ahead and skip like the first 2 minutes, minute and a half of the second one that you observe. Alright, now the reason I have this intro part is because I'm going to be able to say this sort of two things that are going to stick for both of the types of systems you're going to look at. One system is going to be concentric spheres. The other possibility is concentric cylinders. But for both of them, we can always say a couple of things. Number one, let's go ahead and draw something here. Let's say that's a sphere, or maybe actually we could be just looking down the end of a couple of concentric cylinders. I don't know. It's not important. Alright, first thing is that if you want to find, say, the electric field in here somewhere, or maybe you want to find the electric field out here somewhere, the object around your central object is actually completely irrelevant to what you're doing. It doesn't even matter. Because for Gauss's law, all that actually matters, if you recall, is what is inside of your Gaussian surface. So if there's stuff outside of it, it's irrelevant to what you're doing. Alright, the second thing that we can always say in general is that if this middle object has, say, a charge Q, then the inside surface of the outer object, assuming that it's a conductor, is going to have a charge of minus Q on it. I swear that's a Q. That's really a Q. Honest, I promise. There we go. Now it looks like a Q. Alright, that's, again, assuming that it's a conductor, right? Remember, the idea is electrons are attracted inwards towards the charge in the middle here. Okay, so they migrate in. So if this is a positive charge in here, then you get negative charge accumulating on the inside surface of the outer conductor. Alright, for the outer surface of the conductor, it's going to be whatever it needs to be in order that the inside surface and the outside surface add up to the total charge. So if you're looking at Q inside plus Q outside, they're going to equal the charge on the let's call it the conductor. Which, remember, the way I'm doing this, that's always going to be the outer object. Okay. Now, we're going to have to apply these in specific circumstances, but these are a couple of rules that we can generalize. Now, let's apply what we saw in that intro to the case of concentric cylinders. If you want to follow along with the text here, meaning like have it printed out, be able to write it out, it's in the Google Drive. You should be able to find the file that contains this example. And if you want to see spheres, that's going to be the other video that's also in that file. So here I recorded a little video to go along with the text here of me working it out, which I'll pause and explain from time to time. This is just me drawing the system that's being described. Okay, so it says you've got a thin rod with a charge density of lambda, and it's placed inside of a hollow conducting cylinder, and then there are its inner and outer radii. And for the first part, we're finding the charge on the conducting cylinder's inner surface. Please remember, lambda is not a charge. That's a charge density. Anytime you want to express a charge, that's a Q, and you have to actually calculate it based on what the charge density is. So, in the case of lambda, that's a very straightforward thing. If I gave you a sigma, that might be a little bit more involved, I mean. All right, now I wrote a lie there up at the top, which I'll eventually acknowledge. But the correct thing that I should look at is if this is lambda L for its charge, that means the charge on the inside surface is the opposite. Remember, please, they must match. That's how it's always going to go. So if this is lambda L, this one's negative lambda L, assuming, of course, that it's a conductor around them. All right? Now, I wrote there something that's kind of true, although it's not for this particular question. If the conductor were neutral, that would mean that the charge on the outside surface would have to be positive lambda in order to cancel out to 0. But as I'll mention when we get to like part D, it's actually not a neutral conductor, like not at all. All right, let's keep going though. If we want to get the electric field, it says R is less than A. I'm going to assume that means outside of the rod, because if it's inside the rod, then it's going to be a totally different matter. Oh, let me get my hand out of the way. There. No, pause. All right. No, it's back in the way. There. Now, for that, it's Gauss's law. Applied, like, notice, as I said, it's applied as you normally would for just outside of just a single object, right? As long as you are, say, in this region, right, surrounding the rod in the middle, right, and you haven't, say, ventured out into the conductor doesn't matter, because that's the beauty of Gauss's law, right? Q enclosed means we're just talking about the stuff that's actually inside of the Gaussian surface. If it's outside of the Gaussian surface, nobody cares. So this outer conductor is irrelevant, only this inner one matters if you're trying to find the field, say, somewhere in here. All right, now, so we've done this derivation before. You can find that in example 16 in your notes packet, part F. Isn't any different from anything we've done before, so I don't think we need to necessarily go over it in extreme detail. All right, now part C, explain why the electric field is 0. It says for R is between A and B, so that's in here. You should know the memorized answer. It's inside of a conductor, Mr. Errico. That is true. However, you should also know the reason, which is being expressed right here. The reason why it's always 0 is because the enclosed charge is going to be 0. This lambda L and this negative lambda L cancel out and give you a grand total of nothing at all. So therefore 0, and therefore the electric field anywhere inside of that conductor is going to work out to be also 0. All right, now if we venture on to part D, I have to move this around, and we've got to figure out the charge on the outside surface. All right, this involves talking about what's the total charge on the conductor, which I work out right here. That's just using the same relationship, right? Lambda, we've learned before, is Q over L, so that means that lambda times L is going to be Q. All right, it says the conductor has a charge density of -2 lambda, therefore -2 lambda times L is going to be the total charge of the conductor. That includes both the inside and the outside surface, which is what's being expressed here, right? Q on the inside surface plus Q on the outside surface is going to have to add up to the total charge that's actually on the conductor. We already worked out that Q on the inside surface was the negative lambda L. Therefore, if the total charge is -2 lambda L, some algebra is going to give us that Q on the outside surface is also negative lambda L, because that's how it works out. All right, now, to continue, if we want to find the electric field outside of the system, that's going to involve us, again, like using Gauss's law, as we ought to be accustomed by this point. And there's, again, like there's two ways you could think about the charge enclosed, right? One way is to think about Q enclosed as being the sum of the inner cylinder and the outer cylinder. All right, the inner one has a charge of lambda L. The outer one has a charge of -2 lambda L. That's what's being expressed here for a grand total of -1 lambda L. Notice also, though, that that is the charge that exists on the outside surface. It's how it's always going to work out. The total charge of the system ends up being the charge on the outside surface, as long as the outer thing is a conductor. All right, so if we carry that derivation forward a little bit, a little bit more. All right, so if we look at the result now, you can see, oh my goodness, it's the exact opposite of that one. All right, that's going to be because this charge is positive lambda L and the total charge is negative lambda L. All right, which is going to be an interesting result. All right, now the last part of the question, it says draw a diagram showing electric field lines. This is something I'm not honestly sure that I would ever ask you to do per se, but I think it is interesting. Since the electric fields are equal, all right, equal in magnitude, same function, right? Not even like multiplied by 2 or something, but opposite in sign, that means that the electric fields are going to be in opposite directions. So the electric field on the inside is actually going to be outward because it's a positive charge in the middle. But the electric field on the outside is actually going to be inwards because the total charge is negative. So that gives you then, I don't know, I think an interesting picture, right? Electric fields look kind of the same, right? Same spacing of the field lines because it's the same magnitude field, but different directions because the signs of the charges are different. All right, that's all for cylinders. If you need to look at spheres, then you should consult the other video.